This is the second part of week 9 lecture. The last version I made some mistake and some slides we lost the voice, so I remake this again. The first part we analyze the model of the ideal sampler. This part we're going to address the model for the zero-order hold. So the ideal sampler is from analog to digital, and zero-order hold does the opposite. We get from digital signal to analog signal. Zero-order hold turns the output signal from the controller, which is UK. This is your controller algorithm, into UT, which is this red one. So the difference you can see, UK is black dots, which is only available at those sampling times. So we'll say this is a T, 2T, 3T, only available at the sampling instant. However, our output needs to be driven by a continuous signal. So what do is we fill the blank. In between these dots, we hold the value of the previous instance. And this is why we call it a zero-order hold. So pretty much what it does is at certain time, it holds the value until the next one coming and change the value. We need to get a mathematical model of this zero-order hold and then include this into our transfer function. So by definition, the transfer function of the zero-order hold is its Laplace transform of the output in response to the unit impulse. Let's just look at the shape of this signal. This is like kind of one pulse from t equal to 0 to t equal to t. And if we consider a unit step signal, say if I get a step signal from 0, and then we minus another step signal. Change another color here. Then we minus another step signal, which start from time equal to t. And it's another step. So if we use the first step, the red one, this is our first step input, to minus our second step input, this blue one, and that's our kind of model. So this is pretty much the transfer function, or this is what the zero order does. So we have to do the impulse response of this thing. Okay, how do we get a if we say input is a impulse signal, what does output look like? Okay, we don't derive this too much detail. So what it does is this is basically the we take the Laplace transform, and the result is following. So zero order hold is pretty much just 1 minus e negative st over s. Well, it's easy to see that 1 over s, this is our Laplace transform of 1t, and then e negative st over s, this is our blue one. Okay, so the zero order hold mathematically can be represented by this, and we take Laplace transform, it is this thing. Okay, then in the future calculation, we can take this zero order hold and replace it with let me change the pen here. This thing we can replace with that zero order transfer function. Right? And remember, this is a time domain or continuous time domain function, because the output is a continuous signal. Now we have the transfer function for the zero order hold. How do we use it? Actually, what we do is we combine this zero order hold. This is a transfer function, and the transfer function of the plant, these two together, as a transfer function in Z domain. This whole thing into we call a HZOHZ. So it's the plant is HS, this transformation, including the zero order hold in the Z domain. So after we're doing that, this whole blocks will be a transfer function in Z domain. Our controller obviously is a transfer function in Z domain, and we're going to design that. Our reference with AD converter or the arrow signal, this is a discrete time signal. So if we convert this EK into EZ, then based on this EZ and our controller function, we can generate this UZ to be used to control this HZOHZ. So this becomes a completely digital system. And we're going to discuss that, how do we actually get this discretized controller in next week. But now we've got how to do the sampling and also how to do the zero order hold, how to get the zero order hold modeled in our system. So the plant and the zero order hold can be put together as a single Z transfer function. This is called the zero order hold equivalence of the plant. So doing that is basically straightforward. We're still trying to convert things from S domain to Z domain, but we don't just do it directly. We have to multiply this component before the transfer function of our plant, put this all together, then we do the S to Z transform. So let's look at this. This is 1 minus E negative ST over S multiplied with HS. When we do this part, this top part is actually straightforward. This is basically 1 minus Z minus 1. This is just the top. That's very straightforward. You can find from the table. And then the rest of them here is HS over S. Okay. This is telling why you can get to this part. Where's this come from? Now what we do is we use HS divided by S, then do the same thing as before. In summary, what we are trying to do is trying to model the zero order hold in our system. And because zero order hold is right before the plant, so what we do is we combine these two together and get a discrete time Z domain transfer function with the overall. So that's what we do. And the question now is become here, like how do we do this one? Again, we use a partial fraction, then look up the table to find items that's available for us to read. Here in the table are the three kind of most commonly used items from S domain to Z domain. So this one is integer, double integer, first order system. If you have your transfer function in that kind of form, you can directly read to get the Z corresponding z transform transfer function. We learned two different ways to do this. This is in part 1, and we just mentioned this one in the last few slides. This is part 2. What's the difference? Like, why do you put this in there? Or why do you have a 0 hold? Why do you have 1 minus z minus 1 to get xs over s? Why don't you just do z xs? That's the first part. Where does this come from? Actually, other than these two, we will learn another 3 or 4 different methods actually do this. Each one of this method maintain certain property between the continuous time system and the discrete time system. The first method, this is called a impulse invariance. So it maintains the impulse response of the continuous time and discrete time. So the impulse response of the system when you do this method to do conversion are the same for the continuous time system and discrete time system. However, the second method is when you physically have those 0 order hold, you have like impulse signal output like that, you want to convert that into something like that. Okay, so from that to that, you have physically 0 order hold in your system, and this additional stuff is trying to model that 0 order hold. So one very kind of fixed rules is this second way of conversion is only used when you physically have 0 order hold. So basically, when you have digital output from the computer, want to convert that into a continuous control signal, that's when you use this. That's when you use this. The first way of conversion is when you design a controller. Physically, there's nothing. You just do some arithmetic conversion, trying to maintain the impulse response. We're going to mention a few other methods, at least 3 different methods next week, which we focus on other parts of the we try to maintain other features between the S domain and Z domain. Now let's look at a couple of examples for us to convert from S domain to Z domain. So the first example is we know the transfer function. So you got 3 poles, double -1 and a -2. 3 poles for the system. We wanted to convert this to a Z transfer function, or discrete time transfer function. Sampling time is 1, so we need to have sampling time to be able to do this. So here we use the first method, which without using the 0 order hold. It's the same way as we did in the last week. Partial fraction, that's one of the methods we can do manually. So xs, because you have 3 poles, you can eventually be represented by something like that. You have double -1, so one of them is s plus 1, the other one is s plus 1 squared, and the coefficient a, b, c is to be determined. Then we can calculate that. So the easy way is you just multiply you can multiply all this top with the denominator, you get the same common denominator, then you set up s equal to -1, s equal to -2, or you can get another s equal to say 0. Then you can calculate ABC. So that's all done. If we have question over here, you can go review to the last week's lecture when we do the partial fraction. Then you got these 3 items. Look up from the table. And this is first order, second order, first order. So xz this is all just directly from the table. Okay, it's actually quite hard to remember, so you have to be able to see the table. So in the exam, you will be given a table, and you can refer to the table to find out the relationships. And then we can do some combination. So this is just simplification, which not necessarily you probably don't necessarily need to do. So we can consider this is the discrete time transfer function for that original xs. The second example is, like I mentioned, if there's physically a zero or hold in there, you cannot just directly convert xs to xz. You have to consider there is a zero order hold. So originally we have gs with a zero order hold. Okay, gz becomes this. So gs comes here. You have 1 minus z negative 1, and inside the z you get a gs over s. So basically we have to do the partial fraction for this thing to get the z from the z table. All right, things out there, just leave it there. Okay, so put that gs in here. You got a over s multiplied with s plus a. So this is obviously you got 2 poles at 0 and negative a, and it will be something, the outcome will be something like this form, and you can determine those two constant. So after this, then we look at table. So table item, this one and this one. Okay, you got this and that. Then you multiply 1 minus z minus 1 in there. So you can see because there's top, you get a power z there. They automatically just cancel out with this z minus 1. And you can do a little bit combination. Things can get a little bit simplified. Eventually you got something like that. Okay. So in MATLAB, I recommend you could come to open the MATLAB and type in help C to D. Okay, then it come up with a bunch of options, many of them. The first option is you basically use that xs to xz directly. Then second option is zero order hold. There will be many more, which we will introduce next week. So this is a different way of the converting from S domain to Z domain. And this is used when actually there's some zero order hold physically in the system. So let's summarize. What do we have here? Original digital control system, discrete time system is like that. You have output is a continuous signal, goes back compared to the reference, and you do a sampling, and this is computer to do the calculation and generate certain control pulse that goes to the digital to analog converter, and that analog signal drives the plant. Okay, so you combine with the analog and digital components in there. Now we just learned is actually this bit can be lumped in this GZ. Okay, remember GZ with the zero order hold and the plant. As soon as we did this, you find out because computer here is in Z domain already, and you're planting Z domain, then this will become a complete digital system. Then we can use transfer function in Z domain actually to analyze system and design a controller in Z domain. So let's look at another example. How is that going to be the case? So this example is a control system, feedback system, represent the velocity control of a DC motor. So This one, first order system, this is a DC motor. This thing is the zero order holder. Okay, it's written in there. If you're not familiar, you go back a few slides and check. This is zero order holder. So pretty much you get a reference signal compared to the measurement output, and the arrow here is go directly through to the output and control the motor. There's no controller. So suppose you have a controller here. Okay, you have a say, or just a controller. But in this case, controller just the one. It didn't do any control. Okay, so how do we get a feedback transfer function for this? Okay, so if the question is the input RT is a step input, what is going to be the output? Okay, at a certain sampling time. Then we already know in time domain we cannot do any manipulation here. To address this, because the transfer function GS is equal to, or GS or GZ, or let's say GZ equal to output in Z domain over input in Z domain. Okay, if we know the GZ, we know the input is in time domain is just step, which we can then easily get the Z domain, right? Then if we know the GZ, then YZ can be calculated from the input multiplied with the transfer function. Okay, so that's where we come from. Then the question is, what is this GZ? Okay, what is the transfer function? Okay, if we find it, the problem solved. So we can see the GZ is basically this two box. That's the open loop. Open loop is just this two. Then you get a feedback. Okay, let's do the open loop transfer function GZ. This is just the zero order hold over the GS, which is A over SA. A over SA. Okay, so that's straightforward. And the transfer function in Z domain is this. That's including this whole thing. That's the whole box. Okay, this is only open loop. Then the closed loop transfer function is closed loop is actually this. So this is not exactly right. So this is not exactly right. Okay, this is I consider the complete closed loop. Okay, I should use a different symbol. But the output Y over input R is equal to the closed loop transfer function, which is the open loop divided by 1 plus open loop. Alright, so open loop is this thing. That's all G. So put this in here. That's your GZ in here. And do a little bit of simplification. We'll got something like that. It's little bit complicated, right? Nobody can remember or get used to this. But because this E negative AT thing, I think, but this is just constant. You consider this is just constant. So it's not really so daunting actually. So on the top basically is Z minus 1 with a constant. At the bottom is 1 minus a constant multiplies Z minus 1, a constant. Yeah, so still pretty simple. So when we got this transfer function, the next step is to look at the input signal. That's the input signal. Then output is simply equal to the input multiplied with this whole transfer function. Alright, so pretty much just multiply them together and do a little bit of simplification. We got our YZ is this. Okay, don't be scared by this. We wanted to know the signal in time domain. So eventually we wanted to know YT. So from YZ to YT, we have to do the inverse Z transform, which we mentioned in last week, right? Inverse Z transform. What do we talk about it? We do partial fraction and look about table. That's pretty much it. Okay, so this looks daunting, but actually it's not hard, right? You get a pole at 1 and another pole at this thing. This is just a constant. Okay, looks complicated, but just constant. And we remember when we do partial fraction with this z, we don't partial fraction yz. We actually partial fraction yz over z. That's just a little trick. It always works. So you divide z both sides, then do the partial fraction. Okay, just remember this whole bit looks complicated. It's just a constant. This is just constant. Okay, so don't worry too much. Just be careful and don't make silly mistakes. It's again, you got a and b, two constant in the top, at the top. Then you take z equal to 1 and z equal to this whole thing to figure out a and b. Okay, which in this case is both 1. Then we know multiply z to the both sides, and this 2 item is actually in the table. Okay, this is easy to find from the table. So this is just step. This is simply power of k. Okay, so that's the solution of ykt. You have a step response. It will be something like that. Okay, hard to see. If you put that in MATLAB, you can simulate that. But I know it's not very intuitively to see. We have a few cases of how the system is connected. Depends on where this sampler and system reconstruction thing is. So it depends on where these things are. Okay, so if these two things are connected, there's no sampler in between. When we do the Z transform, we do them together. If these things are separate, for this case, GS and HS are not connected, they're separated by the sampler or 0 or hold, then when we convert to Z domain, we do it separately, then we multiply together. So these two, we multiply together first, then do the Z transform. And these two, we do the Z transform individually, then multiply them together. So the difference is here, if you can see. So output is equal to open loop, which is GS, HS, the output is feed forward, which is RS multiply with GS. Because there's a sampler in between, there's something separating here. So we do GZ, RZ, which is S to Z transform for each individual case. And at the bottom is 1 plus closed loop. Okay, 1 plus closed loop. So 1 plus closed loop is the loop here. In this case, G and H are connected. So you get a GHZ. This means you multiply with GS with HS, then you do a Z transform for the whole thing. Okay? Look at the bottom case. The only difference here is because this sampler is a little bit ahead, is inside the loop. Then separate GS and HS. So the transfer function is still, the output signal is still the input multiplied with forward, which is GZ RZ, divided by this closed loop. So 1 plus GZ and HZ. So just be careful with this difference. Okay, 1 is you do multiply this S together, then you do the Z transform. The other one is for each individual GS or HS, you do the Z transform, then you multiply together. Actually, these two you give you very different answer. 3 more examples here. So all we need to know, be careful, is all these kind of sampling stuff. Okay, let's do it one by one. So in the first case, the output CZ is equal to this whole chain over here. So G1Z, G2Z, and RZ, because all these three things are separate. Just multiply them together over 1 plus the loop. So in the loop, you can see G1 is separated, G2 and H is connected. So G1 is separate, G2 and H is connected. So basically this is, you multiply G2S with HS, then you do the Z transform. Okay, that's the second case. Third case is here. Again, output is equal to the input, multiply with this forward chain. Again, this two is separate. So you get G1Z. Oh, this is different because you see this two is actually no sampling together. So you multiply RS with GS, G1S first, then you convert to Z. That's this part. Then for the G2S, because it's separated, so you do the G2Z separately. And then 1 plus the loop. So inside this loop, you can see G2. They are all connected. So G2 is connected to H, H is connected to G1. So it's 1 plus G1, G2, HZ. So you do these three S domain, multiply them together, then do the Z transform. Okay, because they are all connected. The last case is output CZ equal to forward is this thing. That's what's on the top. So you multiply them together, do the Z transform. And then 1 plus the closed loop. Okay, in here, GS, HS, this part separate, but this part is connected. So they are still together. It's only when they are both separate, like in this case, this G1, in this one, this G1 is completely separate. So in here, it's completely separate. So there's a few cases like this. You need to be able to simplify the block diagram to get the proper digital frequency domain representation of the transfer function.